presentation. So as I was sort of just saying, this is going to be very much work that's in progress. And so anyway, I decided I would talk about it anyway, even though it's still not really finished, partially because I think some of you would be interested in it, partially because I think maybe some of you can help me with some things. Although I guess it'll be a little bit of time before we get to the new stuff. Okay, so this is going to be joint work with Alexei Ilin and Leonid Rybnikov, and about trigonometric Godan algebras. So maybe I'll begin by talking about the regular Godan algebras and some of our previous work on this topic. And then we'll get to the trigonometric part. Okay, so feel free to interrupt at any time with questions or corrections. Okay, so let's start with fix a semi-simple Lie algebra. And let's consider a tensor product, which I'll write like this, V lambda underline, tensor product of irreducible representations of G. So obviously a classic problem in representation theory is to find the decomposition of V lambda into irreducible representations. I mean, of V lambda, I mean this tensor product representation. So one way you could do this, I mean, is to find a basis for each Hom space into the tensor product. So we consider Hom over G from some of your other irreducible V mu into this tensor product. And whoops, I forgot all the other words. So 2 is find a basis for this space. And how might you accomplish number 2? I mean, maybe in different ways, but the way I'm going to talk about now is to find a big subalgebra, commutative subalgebra, or let's say commutative algebra acting on the tensor product, commuting with the G action. And then you could hope that you can diagonalize the action of this commutative subalgebra into one-dimensional pieces, and that will provide your basis of the Hom space. Because it acts on the tensor product commuting with the G action, it will act on each of these Hom spaces. Okay, so how did people do this? I mean, I don't really know the history of this subject that well, so this part of the fact might be a little ahistorical, but let's just imagine how someone might have done this. Well, they started by finding these special operators called Godan Hamiltonians. So they depend on a choice of some complex numbers. So these are all going to be complex numbers, distinct. And then we formed the Godan Hamiltonian. So defined as follows. So there's going to be n of them. The n here corresponds to the number of factors in this tensor product. And so for the ith one, we sum over all other tensor factors, j not equal to I, and we insert the Casimir in the I and j spots and divide by zi minus zj. So this omega is in G, tensor G is the Casimir. And this omega to the upper ij means you act with that Casimir on the ij spots. So these guys commute these guys, first of all, commute among themselves, commute among each other, and also with the diagonal action of the Lie algebra on this tensor product. And so they defined a commutative algebra acting on each of those Hom spaces. And when G is equal to SL2, this is enough stuff in order to diagonalize those Hom spaces and find a basis for them. But for other G's, this is not enough. So people had to expand on these guys so that then we get the following theorem. So one is that for any Z in Cn minus delta, so Cn minus delta is going to be those n complex numbers that are distinct. There's an algebra called A of Z, commutative algebra, I should say, commutative algebra A of Z, and it sits inside the n-fold tensor product of UG with itself, therefore acts on such a tensor product, and also commutes with the diagonal G action. So I put this superscript G to indicate that. So commutative subalgebra of UG tensor n commuting with the diagonal G action, which contains these Godan Hamiltonians and other stuff. So I guess I should say I don't quite know who to attribute this point number 1 to, but let me say that maybe okay, maybe Valerio can tell us. But anyway, maybe
Fagin and Frankel and Reshetikhin, right?
Yeah, Fagin, Frankel, Reshetikhin. Thank you. I think I had the name Reshetikhin wasn't getting out of my head. So.
And it's a maximal commutative algebra, right?
Yeah. So it's a maximal commutative subalgebra of this thing. And yeah, I should say the definition of this the definition of this Godan Hamiltonians, well, that wasn't very complicated. The definition of this thing is much more complicated and involves the center of the affine Lie algebra at the critical level. So then that's somehow the first part, and then the rest of these parts are more related to our work on this subject. So, well, sorry, maybe there's not, but anyway, for all such Z, this algebra A of Z acts cyclically on this Hom space. So that indicates that it's, oops, that's good. In fact, like there's a cyclic vector for this action. The next part of the theorem is that for real Z, this algebra is generated by Hermitian operators with respect to the natural Hermitian structure on the tensor product. So because it's generated by Hermitian operators, we can simultaneously diagonalize the action of A of Z. And because it's cyclic, the action, there can't be any repeated eigenvalues. So the combination of 2 and 3, it shows us that there is a basis. So 2 and 3 shows us that there is a basis. There's a decomposition of this Hom space into one-dimensional. You could say one-dimensional submodules to the action of Z, or one-dimensional eigenspaces action of Z. It's the same thing. I would say eigenspaces. Or again, when we have real parameters. Now, further development is that, so this, from number 1, we have a map from Cn minus delta to the space of subalgebras. Again, maximal commutative subalgebras, but in particular subalgebras of this guy. And it's easy to see that this, the algebra of Z doesn't depend on if you simultaneously scale the parameters in Z, nor if you simultaneously add something to all the parameters. So you can mod out here by C cross times C, so we direct C. And then you can think that this Cn minus delta mod this Borel subgroup, C star mod semi-direct C, is the same as P1 to the n plus 1 minus delta modulo the action of PGL2. So PGL2 is now a three-dimensional group. Use 1 degree of freedom of the PGL2 to move 1 point to infinity, and then you're left over with this Borel subgroup acting on Cn minus delta. And then you think that this space of P1 to the n plus 1 minus delta mod PGL2, that's a moduli space of n plus 1 points on the projective line. And that has a natural compactification, this Deligne-Mumford compactification. So this thing sits inside 0 n plus 1. So this is bar. So this is this Deligne-Mumford space of genus 0 curves with n plus 1 marked points. So in this space, let me just draw a picture of a curve in this space. So it has, the marked points can come on different components. So this is a point, this is a picture of a point in the boundary of this space. So it has some marked points, possibly on different components. So in the sort of open part, which is this part with the P1 to the n plus 1, here we just have n plus 1 points and P1, but then as some of the points start coming together, we get points in the boundary. Okay, I didn't finish number 4. So number 4 is that this map extends to a map like this. In fact, even an injective map. In other words, the space of all limits of these Godan subalgebras, so this algebra is called the Godan algebra, the space of all these Godan algebras is isomorphic or is equal to this moduli space of genus 0 curves, marked genus 0 curves. Okay.
So not just injective, but bijective then, you're saying?
Well, there may be some subalgebras, even maybe some commutative subalgebras which are not of this form, but all the ones which are obtained as limits of ones of this form are at this space. Okay, so I guess I didn't really give a good attribution to 2, 3, and 4. I guess I guess 2 and 3 are probably due to Rybnikov, and then 4 is in our paper building on work of well, other people. Let me not try to say everybody. Okay, anyway.
So in for 3, can you say something about the joint spectra?
That's this part. Oh, well, I'm about to say some more stuff, maybe.
Okay.
Okay. So if we're combining, okay, let's go back to the statement then again. So remember 2 and 3 gave us a decomposition labeled by these real points, n distinct real numbers. And now we can extend that to the moduli space M0 n plus 1 bar R. And that's very good because this moduli space has an interesting fundamental group. So let's define the following thing. So E lambda mu Z. So for Z in M0 n plus 1 bar R, that E of lambda mu Z be the set of eigenlines. So all the eigenspaces are one-dimensional. So eigenlines for the action of A of Z on this Helm space. And now we can consider this is going to be a covering So this is a covering of topological covering of our modular space. And so it's interesting to understand the monodromy of this cover. So to formulate this, our theorem about this monodromy, we're going to study the fundamental group of this modular space, and that's going to be a group we call the Cactus group. So let Cn be the group, just abstract group with generators as follows. So Sij, where I and j run from 1 to n, one is less than the other, which we think of the generator as being associated, so 1 to n, maybe some I here, j here, and we think of the generator as being associated to the interval between I and j. So those are the generators. And then oops, the relations in this group are as follows. Sij squares to 1. Oh, and maybe I should say another thing about this generator is we think of it being associated to a symmetric group element. The symmetric group element is the element of the symmetric group, which outside this interval is just the identity. So as a diagram of the permutation would look like this, and inside it is like the long element. So it goes like this. Okay. And okay, so those guys square in the symmetric group. What I'm writing here is like some of the relations that these things satisfy in the symmetric group, but not all the relations. Otherwise, we just get the symmetric group. So the second relation is that the generators commute if these intervals are disjoint. And the third relation is that if one interval is contained inside the other interval, then the outer interval will conjugate the inner interval to the place you might expect it to. So it's given by the following formula. So we have like an outer interval and then an inner interval. So this outer guy is the ij, and the inner guy is the kl, and then it just gets flipped to this other interval written here is just like the result of flipping this kl inside the interval ij. I plus j minus l, I plus j minus k. So this is a group, an infinite group. It has a map to the symmetric group, which takes the Sij to that permutation that I drew above. So we think of it as an analog of the braid group. So braid group is also an infinite discrete group with a map to the symmetric group. But this one has different than the braid group. It has more generators and it has some slightly complicated relationship with the braid group, which is not that relevant. So I won't talk about it. And then maybe we call it the Cactus group. So why is it relevant for us? Well, I'm going to present two theorems about this Cactus group. So the first is that the Cactus group is the fundamental group of the modular space, or slightly more precisely, the equivariant fundamental group. We have to divide this modular space by the action of Sn. I mean, equivalently, you could define the pure Cactus group to be the kernel, and that's actually the fundamental group, but simpler just to think about this, better to think about it like this. Let me see. And how does it work? Well, I mentioned that the point in this modular space looks like a possible union of these P1s with some marked points. So imagine we have the following curve inside the modular space. So I'm going to start out with some base point where I have my points ordered in the usual way up to n. Then I'm going to pass through a wall. So maybe it was obvious or knew this already, but before we took the compactification, if we just looked at Rn before we took the compactification, so if we were just studying back here, the this Rn minus delta, that space is disconnected. It has something like n minus 1 factorial connected components, maybe n minus 1 factorial over 2 connected components. Anyway, depending on after you mod out or something. But anyway, it has plenty of connected components. And so when the way we'll think of this convectification is that there are these open parts, and then we have some walls separating them. So now we're going to see what happens when we pass across a wall. So here we are in one connected component of the original space. Now we have a wall. So what's going to happen on this wall? So on the wall, all these points on the interval I to j will come together. They're starting to move closer and closer together. And on the wall, they bubble off onto their own component. So we have the points from I to j over here. And then what happens is that, well, this curve has an automorphism which flips the second component and leaves the first component alone. And that reverses the order of the points from I to j. So that when they can then pass through, you can pass through this wall as you're moving in this moduli space and get to the other connected component where the points from I to j have reversed in order. So there we are at another connected component. And so this path from here to here, this is going to be this element Sij of the Cactus group. So it's not a loop in the moduli space, but that's okay because of this modding out by Sn business. So it's okay that the generators of the Cactus group give us not loops, but these little piece of paths in the moduli space. Okay, so this theorem I guess I was a little sloppy before with attributing. This one I can attribute properly. It's due to Davis, Januszkiewicz, and Scott. I hope I spelled the same way. Okay, now so this is all very well. So we're interested in that. So we get, in other words, from this theorem, we get an action of the Cactus group on this space of eigenlines for our Godan algebra. We want to understand that combinatorially. So in order to do so, I'm going to explain now about theory of crystals. So there's a combinatorial analog of the category of representations of G. Analog of G, and it's the category of G crystals. So what's a crystal? I won't give a definition, I'll just maybe show an example. So here's an example. Imagine that we're considering G to be SL3, and we're considering the V lambda to be the adjoint representation. So it's SL3 acting on itself. It's an 8-dimensional representation, and its weight diagram looks something like this. You have all these 1-dimensional weight spaces, and in the middle here you have 2-dimensional weight space corresponding to the 2-dimensional diagonal trace theorem matrices. And a crystal is a way of putting a graph structure on this set of dots I've drawn, and the graph structure in this case looks like this. Oops. Maybe I should have made these 2 dots slightly further apart, otherwise it's going to be hard to tell. Okay, there we go. Graph structure looks like this, maybe. You could, I don't know. You don't have to use different colors, but I guess it's nice. So that's a picture of the crystal. So it's a graph whose vertices are a basis of the representation V lambda, and the edges correspond roughly to action of the Chevrolet generators of the Lie algebra on that basis. And so this guy is purely combinatorial object is called B lambda. Sorry, no underline. And in the case when in general, when G is equal to SLN, there's a nice model for B lambda as semi-standard Young tableau of shape lambda. So in this example here, maybe we would have the tableau here, 1, 1, 2, and here the tableau 1, 2, 2, and here, there, and so on. Okay. What can you do with these crystals? Well, if you have, again, there's a crystal associated to every irreducible representation of G, and there's also a way of forming a tensor product of such crystals. So you can consider a tensor product of such crystals. The definition of tensor product is highly non-trivial. This is the sort of most interesting part of the theory, but I won't go into it today. So this is a kind of non-trivial definition. One thing that's non-trivial about it is that if you have two crystals, B and C, B tensor C and C tensor B are isomorphic, but not in an obvious way. There's a like non-obvious isomorphism between them, which we defined with Andre Henriques, called the crystal commuter. So as a set, B tensor C and C tensor B are just their Cartesian products, but the map between them, this bijection, isomorphism of crystals, is not just the usual map for Cartesian products. Like B comma C goes to C comma B. So again with Andre Henriques, back in grad school with Alan, we proved the following thing, that the category of G crystals has a structure of a co-boundary category. So that means it has a tensor product, and the tensor product has this commuter satisfying certain properties. And moreover, when you have such a co-boundary category, this means that there's an action of this Cactus group on such any tensor product of crystals. Technically, it's like really the Cactus group switches the factors, so it's not quite an action on the tensor product itself, but on all permutations of the tensor product, but it's a short form I'll just write on the tensor product. So now, you probably, well, maybe you already knew the theorem, but anyway, you're probably gonna, even if you didn't, you might be able to guess what I'm about to say. So let's just back up a second. So let's see where we were. So we started by, we were studying this tensor product multiplicity space. On this tensor product multiplicity space gave us a covering using these Godan algebras. We got a covering of the moduli space of n+1 points on RP1, where the fibers were the eigenlines of these guys. This moduli space, in turn, we're interested in the monodromy group of that covering. In other words, that monodromy is going to be an action of its fundamental group, and its fundamental group is our Cactus group. And then our Cactus group shows up now in a purely combinatorial framework acting on this set. Okay, so this is just a set with an action of this Cactus group. So this sets the stage for the theorem that we proved. So it's with Eva, self, Rybnikov, and Alex Weeks. So there's the bijection between the fiber of this cover at some fixed base point, doesn't matter where, and this crystal tensor product multiplicity space. So it's just, you just take Hom in the category of crystals between your crystal B nu and this tensor product crystal, compatible with actions of the Cactus group. So here we have the Cactus group acts by this co-boundary structure with a commuter, and here the Cactus group acts by monodromy. Okay, so that's the end of the old story. Any question about that?
I'm still curious about the joint spectra.
What do you mean by the spectra exactly?
So let's fix your point in the simplex. And then you have all of these operators acting with real eigenvalues on your joint eigenlines.
Yeah.
So each joint eigenline is defining a point inside some Rn, and you get this cluster of points, which is 1 point for each of your eigenlines. What does that big cluster of points look like? Is it lattice points in a polytope, for example?
Well, in the case when, for example, for SLN, like by Mukh and Tarasov-Varchenko, you can identify it with the solutions of the Schubert problems. So in SLN, there's a good answer to that question. Tensor, in general, you have to pick some kind of generators. Maybe there's not really a canonical choice in this generators.
But Joel, maybe one can say that Fagin, Frenkel, and Reshtikin determined the spectrum of this commutative algebra. Oh
yeah, that's true. Sorry, you're right. Of course. Yeah, of course. In general, there's a bijection with a space of opers. Yes, thank you.
It's an appropriate space of opers with regular singularities at the mark points, and then a global no monodromy condition.
Yeah. Okay, so now on to new stuff. Okay. So let's begin as follows. So let's choose a theta in the dual of the Cartan subalgebra, and let's let m theta be the Verma module with highest weight lambda. So highest weight theta. And we have a highest weight vector in this guy and a linear map dual to the highest weight vector. So that just takes the highest weight vector to 1 and kills all the other vectors. So what we're going to be interested in now is taking such a Verma module and tensoring it with our tensor product, and then taking Ham from another Verma module into there. So why is it interesting? Well, first of all, Ham over G. So first of all, Ham over from a Verma module is the same as highest weight vectors in the place that the Ham is going to. So this is the same as highest weight vectors in this guy. Highest weight vectors means invariant under the n, little n, big N, of weight theta plus mu. So highest weight vectors of weight theta plus mu. And if we have such a highest weight vector of weight theta plus mu, we can sort of pick out the component that sits against the generator of the Verma module. So in other words, we map, there's a map which will give us a vector of weight mu in the tensor product of V lambda. So this map here takes some vector here to, we just pick out the highest weight vector out of pick out the highest weight vector in the Verma module m theta. I kind of said that badly, but anyway, hopefully you've seen this kind of construction before. Okay, so that's a map, and this map is usually an isomorphism. For generic theta, so why is this good? Then the reason is as follows. So now we can study the action of a Godan algebra on the left-hand side here. So we have the action of the Godan algebra. I'm going to always choose the first sort of index, first z to be 0. And then we have the leftover z's. So here, this Z is again just Z1 up to Zn, but now Zi's are not Zij's and also Zi's are not 0. So given such n non-zero distinct complex numbers, we have a Godan algebra which acts on this space. And therefore, at least for generic theta, and therefore it also acts on this V lambda mu. And how does this action look? Well, mentioned the one thing you can say about the regular Godan algebra is that it contains these Godan Hamiltonians, and this algebra contains some trigonometric Godan Hamiltonians, so it's actually contains trigonometric Godan Hamiltonians, which I think are roughly like as follows. I might make it. So it looks a little like our old friends. So again, we have one for each I. And then we have another term, which looks something as follows. So it depends on theta. So I'm writing the action on this space here. So on this space here, there's no theta anymore, right? Theta disappeared after we did the map, but the resulting operators in this space will depend on theta. And then I think it looks like this. J, again, not equal to I, omega minus ij. So omega minus denotes the lower triangular part of the Casimir. And then omega I over, sorry, it must be theta I. Okay, anyway, something like this. Doesn't matter the precise form. Okay, so why are we interested in the action of this trigonometric Godan algebra? Here's one motivation. So it comes from completely different source. So let's assume that all the lambdas, so lambdas were the highest weights of our representations that we took the tensor product of. Let's assume all the lambdas, lambda i's, are minuscule. That means all weights of those representations are Weyl orbits of the dominant weight. And one thing this helps us or gives us is we can consider Gur lambda I inside of the affine Grassmannian of the Langlands dual group. So this is a closed spherical Schubert variety. It's actually isomorphic to a G mod P or G check mod P. So for the maximal parabolic subgroup. And then we can form the convolution diagram of these guys. Which maps to this affine Grassmannian. We call that Gur lambda. By the geometric stochastic correspondence, this process of forming these Gur lambda i's and their convolution is related to the representations V lambda I and their tensor product. So in particular, inside the affine Grassmannian, we consider this opposite finite codimension orbits of this group G1 T inverse. And then we pull back by this convolution map to define Gur lambda underline mu M lambda underline inverse of the space. So under the hypothesis I said, this thing is going to be smooth, and in fact, it has a structure of a symplectic resolution. So recently, there's been a great interest in studying symplectic resolutions from various perspectives. For example, this guy is what's called Coulomb branch. And another thing people are interested in about these symplectic resolutions is their quantum cohomology. So that's what I'm about to talk about now. But before then, let's say how this related to our previous thing I was just talking about with the Verma modules. So we have the following theorem of Ginzburg-Riesz, which is a kind of variant on the geometric Satake correspondence, or variant on the derived geometric Satake correspondence. So the theorem is that there is a natural isomorphism between the cohomology of this symplectic resolution, actually equivariant cohomology. So on this guy, we have an action of the torus of our Langlands dual group, T check, and also an action of C star, which acts by a loop rotation. From the viewpoint of the symplectic resolution, the C star action is what's called conical, and the T check action is the Hamiltonian action. And I'm going to take equivariant cohomology for these two actions, but I'm going to specialize at the parameters theta. Theta was my parameter I had earlier, and 1. So 1 in this for the C star equivariant parameter, or you could say H bar. I'll call it 1. So this specialized equivariant cohomology of the symplectic resolution is isomorphic to the vector space we were interested in before. This, I'll just write it like this, of highest weight vectors in such a tensor product of given weight. If you don't want to specialize the equivariant cohomology, you can, it's not a problem. It's just on the right-hand side, you have to work with a universal Fermat module, and you can work with the asymptotic enveloping algebra. Okay. So at least indicates why we might be interested. This is the thing I was just talking about, and we see it appears in geometry. And this theorem, along with some other considerations, led us to the following conjecture. So I don't know. We made this conjecture maybe 5 years ago. It's not published or anything. But, so it's myself and Michael McBreen and Leonid Rybnikov. So conjecture is that there's an isomorphism between the quantum cohomology, again, the same specialization of this symplectic resolution, and the image of A of Z, or A of 0Z, we call it, in that space. The endomorphism of that space. Okay, so on this vector space here, we have this big algebra acting, this Godan algebra, and I take its image in the endomorphisms of that vector space. And my claim is that that image is isomorphic to the quantum cohomology, and not just like sort of abstractly isomorphic, but I mean isomorphic in such a way compatible with the Ginzburg-Riesz isomorphism. So this quantum cohomology acts on the ordinary cohomology, and by definition, this thing acts on, well, the space on the right-hand side of this Ginzburg-Riesz isomorphism. And so here I have this Ginzburg-Riesz isomorphism. So this conjecture, oh, sorry, I should say one thing. You might ask, there's some Zs here and no obvious Zs appearing here. So these Zs appearing here are related to the quantum parameters of the quantum cohomology. So to be more precise, inside there's some quantum parameters which depend on elements in H2, and there's some, you can define, say, Q to this beta ij, and this will match Zi, Zj inverse. So there's a precise matching of the quantum parameters and the parameters here. So this conjecture was partially confirmed by Danilenko. So the theorem of Danilenko is as follows. It's not quite how he stated it, but he stated it as follows. So he wrote the following. So for generic theta, we identify the cohomology of this simplex resolution with the vector space v lambda mu as follows. So his identification takes the stable basis. He just wrote down, say, I'm going to make a vector space isomorphism by taking this basis to this basis. So his isomorphism takes the stable basis to the obvious basis of the tensor product. So remember, each representation in this tensor product is minuscule, so it has a natural basis. So the tensor product has an obvious tensor product basis. And he said, I'm going to take the stable basis to this tensor product basis, and then I'm going to calculate the quantum multiplication by divisors on the stable basis. And it claims in math. So let's write it down. We had by this and the quantum multiplication by divisors matches the action of the trigonometric Godan Hamiltonians. Again, where the parameters are related, as I said in that conjecture. So in that way, Danilenko's theorem is the quadratic part of this thing. So these trigonometric Godan Hamiltonians, they live in here as the simplest piece of this thing, the degree 2 part of this, and this quantum multiplication by divisors, of course, lives here. These divisors live in the 2H2. So this theorem of Danilenko is the degree 2 part of this conjecture. Modulo one thing, you might worry that this like identification was just sort of random, like why stable basis goes to tensor product basis. But actually that's fine. So it's not written anywhere, but it's not hard to prove that that if we consider the following diagram commute. So here we use the Ginzburg-Riesz isomorphism. And here we have this guy's highest weight vectors of weight theta plus mu. And then here we use what we wrote above, this alpha theta, which is an isomorphism for generic theta to go to the weight space in the tensor product. And here we use this Danilenko, again, which is defined just by matching bases. This diagram actually does commute. So this commutes. Okay, any questions about that?
A very naive one. Is there always an action of quantum cohomology on ordinary cohomology?
Yeah.
Huh.
Well, always, I don't know, but I believe so, yeah. I mean, quantum cohomology as a vector space, it just relates more to ordinary cohomology, and the action is just given by multiplication. At least that's my understanding. Okay, maybe what there's not always is what there's not always is in general quantum cohomology, like there's some series involved, and I think those series don't always can't be expressed in series in these quantum parameters, and those series can't necessarily be expressed as rational functions. So here we're using something somewhat special, which I think is not proven, but it's so you can say it's part of the conjecture. Okay, so this was all a motivation for trying to study this trigonometric Godan algebra. So now we'll turn to the kind of thing we did with the usual Godan algebra, considering the monodromy. So again, we have this action of a 0 z. So zi's are again a distinct complex, non-zero complex numbers. So acting on this space. So what will we do? Well, with the following term. Assume that theta plus half of mu actually is imaginary. So it lies in the imaginary part of the, purely imaginary part of the cartons of algebra. And zi's lie in the unit circle. U1, unit circle. Yeah. Then there's a Hermitian form on our vector space such that A of z, or A of 0z, again, same algebra, is generated by normal operators. So this is analog of, well, when I started the talk, we didn't have any theta parameters, so there was no condition like this, but we had real z's, and now I'm using a different sort of real form. I want them to be on the unit circle. I should say that like this whole so this is a new result, and this whole investigation is maybe there's a strong analogy between these trigonometric Godan algebras and what's called beta algebras and Yangians. There's a how-dual relationship. So a version of this theorem was already proved by my collaborators together with, maybe I don't know, Mashanova, Golikova. Just aside. So they proved an analogous theorem, which is on the archive. So analogous. For beta subalgebras of the angles. Okay, so this suggests we should consider some monodromy of this real locus. So what real locus?
Can you say a couple of words about this Hermitian form? Because in the previous case, in the rational case, the Hermitian form was just just a very simple one, right? So how sophisticated is this one?
I guess I can't say too much about it because it's more Linus construction, but yeah, it is more involved to definition, yes, but I can't I couldn't off the top of my head explain it.
Okay.
So in this way, we're going to, instead of studying we're going to end up with a different real form of our moduli space. So we're going to study the following space, which I do not like this. So M0 n plus 2 bar U1. So this is the following thing. It's the compactification of the following space. So I take n plus 2 points on P1. Sorry. I take n plus 2 points on P1 over the complex numbers. They're distinct. The complex conjugate of the 0th point is the n plus first, sorry, not the complex conjugate, but the complex conjugate inverse of the 0th point is the n plus first point, and the complex conjugate inverse of the ith point is the ith point, where I is not 0 and n plus 1. And then we mod out by the unitary group, which is the automorphism group of this real form. And so so this moduli space, by using this U2 action, you can make Z0 to be the point 0, Zn plus 1 to be the point infinity. So you end up with the compactification of U1 to the n. So those are the remaining points minus the diagonal modulo U1 acting by simultaneous multiplication. And the compactification is just like in the, I mean, it is inside the usual Deligne-Mumford space. These real forms, or, you know, there's obviously, you could imagine not just taking 2 points here, but taking other pairs of points and so on. These real forms were actually studied by Özgür Seyhan some years ago. So he like classified these real forms and studied their component strata and so on. But I think this is the first use of such a real form that I know about, real use of it. So here, I mean, here's a very easy example. If we just take M04 U1, well, maybe not too surprisingly, you get still a circle, but it kind of looks different than the, I don't know, usual circle that you get from M04. What happens? Well, so a generic curve, generic thing, here you have your P1, and now I'm sort of going to draw it, I don't know, the following way. So I have two points on the U1. So this red curve will now be U1, not the RP1 we had before, but this U1. I have 2 points on U1. And then I have 2 other points like the 0 and infinity point. I'll just put them inside. I mean, it's really like a sphere, but just to simplify the picture, I'll just put them inside. And then, okay, these two points move around. And so the moduli space is a circle with them moving around, but then when they come together, they go on their own component, something like this. So here are those 2 points, and then here I have my 0 and infinity points on this curve. So that's a picture of this moduli space. So this moduli space has a different fundamental group. In fact, its fundamental group is called the affine Cactus group. So ACN, affine Cactus group. So this is a group generators as follows. So Sij, but where I don't demand that I be less than j, just any ij. And how do I think about the generator Sij? I associate it to it, I think of the points 1 up to n on the unit circle, or on a circle, I don't know, unit circle, but on a circle. And then I consider, you know, put I here and j here, and then I will associate to the generator Sij an interval along this cyclic order, like so. So before I had the points on a line and I had an interval along the line, now I have the points on a circle and an interval around the circle. So like when I is less than j, it looks like the old interval, and when I is bigger than j, it's like some new interval which goes around where they wrap around. And the relations are as follows. How am I doing on time? Oh, I'm almost out of time, I suppose. Okay, sorry, I'll wrap up in a second. So the relations are, well, what you might expect if you like this business. So the generator square root of 1, they commute if the intervals are disjoint. Let me just say it in words. And when one interval is contained inside the other interval, we have the same flipping relation. So disjoint commute. And containment flips.
And you're not taking the whole circle for a generator.
Yes, and we're you're right. I should have disallowed. Yeah, not allowed to. No, actually, sorry. There's no reason. No, you can take the whole one starting at 1 and ending at n is allowed as a generator. In fact, there's 2 ones. Like S1n is allowed and SN1 is allowed.
Okay, I guess I meant S11, which is allowed. Sorry.
Yeah. Okay. S1. Yeah. I is definitely different than j, but you can take S1n and you can take SN1. Yeah, but I is different than j. Yes, you can't take the whole. Like maybe it's an interval along with a sort of direction along the interval. So these two sort of correspond to different intervals. Okay, so then So the theorems then are what you might expect. First, that the fundamental group of this moduli space is equivariant fundamental group, is this affine Cactus group. And this is just a special case of like a more general version of this Davis-Janusz-Scott theorem, which applies to these De Concini-Procesi compactifications in general, and Cactus groups of other types. So this is like the Cactus group associated to the Dickon diagram of type affine AN. So it's just the general result. The second theorem, maybe it's slightly less expected, at least I didn't realize it before, but that there's Cactus group acts on a tensor product of crystals, but not by crystal automorphisms. By crystal automorphisms. So the original Cactus group acted by crystal automorphisms, but this one acts not necessarily by crystal automorphisms. In particular, if you have, how does it work? Well, if you have one of these ordinary intervals, like I less than j, well, you do what you did before. And if you have I is bigger than j, then you just rotate your tensor factors until they're in the right order, and then you apply your Cactus group element. So I don't know how to write it, but if you have something like so here they're in the wrong order. So you just rotate using just the map of sets, which just sends one guy to the end, so on, until they're in the right order. And then you apply your usual Cactus group guy, this S1, whatever, and then Bj goes here and Bi goes here, and then you rotate back. So this is the overall, this is the action of Sij if j is smaller than. And that gives you an affine action of the affine Cactus group. And then then the theorem generalization of the previous monodromy result, or extension of the previous monodromy result, would say that there's a projection between this tensor product of crystals and the eigenvectors for A0Z on this space and compatible with the affine Cactus group actions. And I should say that like the main, if I have like 1 minute left, something, the main tool we use in this theorem is a degeneration of these trigonometric Godan algebras to some other algebras called inhomogeneous Godan algebras, which already appeared in our previous work. And geometrically, that seems to be related to a degeneration of this moduli space that I've been talking about. Let me just write this down because it's maybe the main point. Okay, so this is the idea of the proof. So in order to compute it somehow, we compute the monodromy after this degeneration. So we have the degeneration of these trigonometric Godan algebras. To inhomogeneous Godan algebras. And geometrically, on the moduli of these things, this is a degeneration of this moduli space of n plus 2 points on P1 to, this is the part I wanted to tell you about, something which we could write FMN, and I just don't know, I'm curious if somebody knows whether this thing has appeared in the literature. So this is a moduli space of a curve together with n plus 1 marked points plus one more special marked point which carries a vector, maybe a non-zero tangent vector or a non-zero section of O of 1. So that's why we call it kind of framed moduli space because of this vector. And already this appeared in our previous work, but I'm just curious whether this family degeneration has appeared anywhere before. So if somebody knows, please tell me. Okay, that's all I have to say.
Great, thank you, Joe. Let's thank Joe for the great talk. Cool. Sorry, maybe I'll start with the question. It's a bit of a naive question, but so in this Danilenko and Ginsburg-Rich relative diagram picture that you drew, do you know a priori that alpha theta is an isomorphism, or is that something that?
Well, this alpha theta is the alpha theta that appeared here. It's just this elementary thing where you just where you just project away from m theta by taking the coefficient of its highest vector.
Mm-hmm.
And that this is almost like this. Well, that's why I said here. It's an isomorphism for a generic theta.
Oh,
I mean,
I
I was a little lazy. You can write down maybe more precisely exactly when it's an isomorphism, but it's not hard to find when it's an isomorphism. Somehow, from our perspective, it doesn't matter that much because we're just going to fix some generic theta throughout this part. So it doesn't matter that much for us exactly the value of theta. Well, it has to satisfy this condition also.
Okay.
This condition here.
I see. But what you're using it for is getting to the lambda, so the mu weight space, and so to the crystal picture for V lambda mu then?
Yeah. I mean, ultimately, this thing with the, ultimately, who cares about this tensor highest weight vectors and the tensor product with the Verma? What we're really interested in is this weight space and the ERAB. So that's like, this guy is just an intermediate object. But the point is that by thinking about this intermediate object here, there's no way you could see the action. Well, maybe not no way, but the easiest way to think about the action of this algebra is to have it act here and then transfer the action to here using alpha theta. So the result, this vector space doesn't depend on theta, but the action of the algebra will depend on theta.
I see.
So after applying this isomorphism, we have this action of this algebra, which is just an ordinary Godan algebra, but its action now depends on theta, and that's why we call it a trigonometric Godan algebra. Okay.
Okay. And if you just if you don't take highest weight vectors for theta, and I mean for this theta and mu, if you just think about it as acting on the tensor product? You mean
if you just think it here, yeah?
Is that, yeah, is that the, it's a vague question. Also from the Godan algebra action perspective.
Well, I think you don't, I mean, if you go back already here or something, I never thought about this that carefully, but I think that like for generic theta, this thing will decompose into a bunch of these Verma modules. So
I see.
So there's nothing here besides these, like this highest weight space is just, each of those highest weight spaces just generates a Verma module. So there's nothing that interesting there besides the highest weight vector.
I see. Okay, thank you. Any other questions?
Could you say a bit more about that degeneration of M0 and bar?
Unfortunately, not that much, but this is what I'm trying to understand a little better now.
So on the left, you've got
intuitively, these 2 points are somehow colliding together and then producing a tangent vector there. But this part, we still don't know how to make it that precise. Like algebraically, we can kind of see this degeneration of these algebras, and in coordinates, we can see what's happening. But I don't have a good like understanding of this degeneration, no.
Okay.
Have you ever seen anything like that?
Well, I mean, the idea of allowing specific 2 points to collide and then retaining that information is reminiscent of like a Hassett space,
Okay.
or like moduli of weighted stable curves.
Hassett space. Okay.
Yeah. So that you add weights to all of the marked points, and they're allowed to collide if their weights are low enough, right? And so you take these 2 points that you favor and you give them low weights so they can collide with each other.
But do you remember information there like this then or not?
Yeah, well, so that's the thing, is that the tangent vector is this extra bit of information that that's the mysterious part to me. And so, yeah, I guess I was trying to understand exactly what the squiggly arrow is.
I mean, the squiggly, like technically there's a family over A1 whose fiber away from 0 is this and whose fiber at 0 is this.
Yeah, okay, I see. Yeah.
That's
Okay.
the squiggly. That's precisely what the squiggly arrow means. But
Yeah.
I don't know. I don't quite know how to construct that family. So that's what I expect anyway. But I'll look up this Hassett space. Maybe. And now that you mentioned, I have heard of those things. So yeah, maybe it's the right thing.
Thank you.
So, Joel, I want to ask this affine Cactus group action. Does it go with some categorical name? So earlier you had a co-boundary category, right? With just define a Cactus group, so to speak. And is there a name for this kind of this?
Yeah, I think that we would have it anytime we had a co-boundary category with a functor to sets. And then it just acts, it doesn't act on the category, it just acts on the images in the category of sets. So I think it's equivalent to that data.
But is this kind of structure already known, or rather to say, if just like a co-boundary category is some kind of analog of a braided tensor category, what would be the analog of this?
It's a good question. I didn't think about it carefully, but I mean, one might imagine. Obviously, you would imagine a braided category with the functor to vector spaces, and then I think, but actually, yeah. I didn't think about it very carefully, but and maybe you're a better position to see this, but it reminds me a little bit of this like work of David Jordan with this action of a double affine Heck algebras, like going back to his thesis or something, which in turn built on, I don't know, some work of Enriquez and others of, and there's something I didn't succeed in making it precise, but it reminds me a little bit of that. So I believe that it's sort of the combinatorial analog of that action, but I don't have any precise claim.
I see. And another question is, what exactly is a statement by in this sort of affine Cactus case by Davis, Januszkiewicz, and Scott? So you take what you take the torus of a complex semi-simple group, and then compactify it in some way. You take the real points, or
sorry. Well, no. Well, maybe there's a statement like that, but no, I was thinking about something slightly different. So this like this U1 to the n minus U1. Sorry, U1 to the n minus delta.
yes.
Over U1. We can make instead consider R.
I see. So you affine operator.
Yeah, minus the affine roots. So this would be, and then here we would have something like the affine Weil group, or affine symmetric group. Symmetric group. So something like this, and then, so then I'm going to apply the usual picture to this affine set. And
Wait. Is what you do? You G-Procesi at every one of the centers? I mean, is that what you mean by usual picture?
yeah.
Okay.
And this there's also something maybe interesting that this is if you're familiar, which I know you are, with like Roman Bezier-Kamnikov's pictures of having T structures associated to each one of the alcoves here. And so I believe also, this is like much more conjectural than this theorem, is that so it's each one of these alcoves of this T structure should be associated T structure in the derived category of coherent sheaves on this resolved affine Grassmannian slice. And then when we cross walls between two of these alcoves, we should have a wall crossing functor, which should be a perverse equivalence, and therefore defines a bijection on simple objects.
Mm-hmm.
Look, Ivan isn't here though, I guess. Expert on this subject. And so I think that this affine Cactus group action on this sets here that we see should also match affine Cactus group action that you would get on simple objects by using these wall crossing functors. I mean, the reason why I meant to mention it earlier, I just didn't have time. But so, but that's sort of an under indication of why you something affine going on, because again we have this affine root hyperplane arrangements. That's what governs these T structures.
Okay.
So, two related questions to one another. Can you compare this affine Cactus action to promotion? And secondly, what if you just have a single B lambda 1 and it's a Kirillov-Reshetikhin crystal?
So it's a good question. So let me try to answer the first one first or something. If you have a single Kirillov-Reshetikhin crystal, well, so okay, well, we have a single B lambda, then as you know, we have this internal Cactus group. So of type G on this B lambda. And then if this B lambda is actually a Kirillov-Reshetikhin crystal, so then we have some kind of Cactus group of the affine type. And maybe if it's affine type, like it's type A, then this affine Cactus group, well, it's the same Cactus group, affine Cactus group we were just talking about a second ago. So this is a KR crystal. And in fact,
so I'm mixing up internal and external.
Yeah, but your question is good because this statement that this affine Cactus group action here can be realized as a monodromy, it's a conjecture. So that was a conjecture in that paper that I mentioned of Ilin, Mashanova, Galikova, and Rybnikov. They studied these beta subalgebras and Yangians, which would act on this, well, not that guy, on the corresponding V lambda. So this having this Kirillov-Reshetikhin crystal means that this V lambda is actually a module for this Yangian. And then inside this Yangian, we have this beta subalgebras. And so there's some monodromy for the eigenvectors of these beta subalgebras. And again, and maybe this is where what Valerio said will come in handy, that we would be interested in here for arbitrary G, we put here arbitrary G, we would be here interested in these beta subalgebras in the real locus, compact real torus. Compact torus. And its compactification. So they would range over such a space. And so this was particularly studied in the SLN case in this paper. And they conjectured that the monodromy of the eigenvectors for these beta subalgebras in the Yangian should match this affine Cactus group action coming from this Kirillov-Reshetikhin structure. And then there should be like a kind of Howe duality between these two pictures, which is not being worked out, but maybe something like a kind of extension of what was in Eva's thesis.
And promotion?
Promotion, but I mean, promotion is related to this internal Cactus group action. Well, I think, but I don't really, yeah. So I don't have any further comment besides what you already know.
Okay.